introduction. I'll be representing my team down at RPI, our solution to this challenge. So disclosure. So when we approached this problem, we really broke this down into three different conditions that need to be satisfied for medical image generation. The first, you need high fidelity and diversity. Secondly, you need to have a good distributional match in terms of image statistics. And thirdly, we want high accuracy in unseen but clinically relevant metrics. So let's start with the first one, which is fidelity. For medical images, you need high fidelity because even the smallest details can be a world of difference. And we've seen in past literature that GANs or generative adversarial networks have really good fidelity a lot of times, but they lack the diversity due to issues with node collapse. So because of this, we turn to denoising diffusion probabilistic models, which have state-of-the-art in both image quality and diversity in a lot of other domains. So there's a lot of literature on diffusion models. I only have time to go over some very basics. They're also called score-based models in the literature. But essentially, if you think that you have some distribution of this case images, and you undergo a Wiener process over many time steps until you noise them completely to just pure Gaussian noise, and then you have some D model, in this case it's P theta, and it's parameterized to observe the reverse process of this and try and mimic it at each time step as a Markov chain. And if you train this enough, then you can eventually get a model that you can iterate from pure Gaussian noise to an image. So the downside with diffusion models is that, especially with high dimensional data, this iteration process can be very expensive. So one of the things we do to alleviate this and make the time constraint is we apply something called linear diffusion, which instead of, you first take a variation autoencoder and then put you use that to embed each image into a lower dimensional latent space, and then you can use this lower dimensional space to iterate the diffusion, which is much faster. Now, one of the other participants already mentioned this, but a lot of this is more of an art than a science. So we took a lot of time to optimize these parameters. One thing that we found important was the compression ratio. You can see here, if it's too high, then you get a lot of loss in the detail on the left here. And another one was actually the loss alarm during diffusion training. We found that we had better results, more realistic texture and ligament formation with L2 loss alarm. So with that, that gives us high fidelity images, and that's necessary for this task, but it's not sufficient. We also need the generated images to be individually plausible, both distributionally consistent in key feature statistics, like Dr. Kelkar alluded to. And to demonstrate this, I'm going to look at something called the log fat-to-glandular ratio as one of the metrics. And that's used to discriminate between these four categorizations of breast. So here we have a synthetic image, and honestly, you can't see it very well, but visually there's nothing wrong. It's highly dense, but there's nothing wrong with it. And you wouldn't think there's anything wrong with it just looking at it. However, if I showed you this, then you'd see a problem. You see that there is clearly a mismatch and a bias toward highly glandular samples in the fake as opposed to real generated or the real data. And this is a huge problem for downstream tasks, and it's not something you see unless you look at the overall distribution. And this is not something, of course, this is something not just with our model that has been coded in other ones. So these, left to their own devices, these generated images fail to match the statistical measures clinically relevant. So classifier, this is our solution. We take some inspiration from classifier free guidance paper, and normally latent diffusion or any kind of diffusion sampling is approximating just the distribution unconditionally. However, with classifier free guidance, you are approximating the distribution condition on a label. And a lot of times this is like a text label or a class info. This is what you get when you see these online in these image generators when you put in a text prompt. However, we decided we can get creative and condition each on a clinical label. And in this case, we use the log fat-to-glandular ratio as well as the area of the breast to guide our inference. So this is the The architecture, don't get bogged down in it for our denoising model, diffusion model. The important thing is this conditioning that we use to embed this clinical information that we use during sampling. So if we use this conditioning during sampling, then we can get really good alignment in these two medical image statistics that we're using, as you can see here. But you might say that the problem is, previously we were just told that there were thousands of these statistics that we needed to match, so how can we condition for all of them? And that's true, but what we found is that there's a high dependence between these different statistics, between a lot of these different statistics. So if you pick the right ones, then you can actually, a lot of the other ones will fall into line as well, which is convenient. So that's key 2. Now key 3 is addressing remaining errors. So once again here you see a fake image that looks like it's perfectly real on its own. However, if you segment just the glandular tissue, what you see in my mouse is these small little bits of noise around the borders of the ligaments. And this can be pretty impactful, even though, once again, you wouldn't see them from the naked eye. And these significant errors, if you look at also the histogram, the pixel intensities in the real, you can see these clearly separated 3 modes for the different tissue types. But the model actually fills in a lot of these with the distance between these modes with a little bit of dead space pixels. And to the model, this makes sense because on pixels where it's uncertain what tissue type it is, it kind of compromises and minimizes the loss by choosing parts in between. But clinically, this is really problematic. So to help fix this, somewhat due to the time constraints of the challenge, we do a lot of classical post-processing. So we implemented a lot of handcrafted filters as well as thresholding operations to remove a lot of this noise. And you can see the result, not all the noise is corrected, but most of it is in this glandular segment. And this is something, if you segmented other tissues and looked through other filters, you'd see other problems that we've corrected. So in conclusion, the images that we generated are accurate both perceptually and clinically, at least more accurate, although they're not perfect. And our success here relies on the 3 conditions that we outlined. However, I think as a whole, the problem of degenerative modeling in medical images is far from solved. To apply this to other domains will take a lot more work. However, I think this can draw a little bit of guidance, ideally, to future work. I'll skip this for questions. So, in conclusion, also, I'd like to thank my team. Obviously, we also had one consult of clinical advice from Dr. Fajardo, and I'd like to thank the organizers, because actually defining this challenge, I think, was a much bigger challenge in and of itself than participating in it. Thank you.
Thank you, very interesting. Any questions from the audience or from the organizers?
I can put up a disclosure longer if you want. So
Sure.
yeah, I was going to put it back up, but I know I kind of rushed through it.
But yeah, very, very interesting. So, I mean, when you have these synthetic images, so I mean, one of the known problems is like you have the broken Cooper's ligaments and things like that. So I'm sure, what are the metrics that are used to see if that's the case?
So I don't know I know that the challengers probably did use a metric to measure those. I don't know what it is. What we did to help facilitate that was we did a lot of it through just fidelity and fine-tuning the model. So like we said, when we use the L2 distance, we found a lot better information. And the second thing we did was a lot of the post-processing. We could fix some of the smaller, especially the smaller gaps in the ligaments, and some of the breakages were actually kind of pixels that were technically glandular, but they were kind of right on the threshold because the model wasn't sure how to classify it. So if we fixed those, then that helped a lot with the formation.
Thank you. Okay, so let's congratulate the winning team once again.